Power. Good morning. All righty. First off, just Michael, do you want to say anything? Okay. Just an opening thought. Michael said that he's been, which is good, getting feedback on the school. And one thought is that there's been a lot of information that's been coming at a fairly fast rate. But at the same time, there are experts out there who already know some of this, and perhaps it's not coming quite fast enough. In my opinion, this is a school, and that's what we're shooting for. But there is a lot of knowledge, and so I want to make a suggestion. We had what I thought was a really fun conversation last night about Lambda Orionis. It was coming thick, lots of questions, but as I thought about it, we sort of switched into conference mode. And conference mode is when somebody asks a question, the person receiving the question has this broad context in which the question is coming, answers the question, and a discussion starts going on up here, and those who don't really know the field have no clue what's happening, and what's going on. That's conference mode. And so what I would like to suggest is that we keep up that lively conversation, but when you ask a question, try to contextualize it a little bit. There's a lot of knowledge out there. Explain what you're asking. And I will try, and we will try as speakers, to maybe even rephrase the question and try to add a little bit to it. And also, I think when you go into conference mode, you also tend to start speaking faster, answering quicker, and everything just starts happening very fast. So we're gonna keep things going at a very even pace, I hope. I found this last night as I was, where are the lights up here? Back here? Oh, there, good. Lights on? Sure. I'm not in charge of the technical side of things here. That's perfect. I found this last night. I was reading an article that Charlie wrote. Charlie's just a great writer, and I always enjoy reading his articles. But this one I thought was fun and relevant for what we're doing. This happens to be a paper that he was giving that was published in the Philosophical Transactions of the Royal Society. I believe Kathy had a paper in the same volume. And so he wrote in the opening, the question of the origin of stellar clusters is an old one. As early as 1785, William Herschel first considered this problem in the pages of these transactions. I love that. It's like, this long royal connection here. When he speculated on the origin of the clusters Messier 80 and Messier 4 in Ophiuchus, Herschel, 1785. More than 2 centuries later, despite profound advances in astronomical science, we find that the question of the physical origin of stellar clusters remains largely a mystery. And when I first read that, I was surprised that Charlie said that, because he, as much as anyone, has done a lot of work in advancing this field. And as I sat back looking over the Alps from my balcony, it strikes me that it is quite remarkable how much of a mystery it still is 300 years later. I mean, yes, we're going to be talking about it constantly, but if you really ask yourself what you actually know about the formation of clusters, not a lot of talk and ideas and exploration, but what we really know, it is remarkably still a mystery. And that makes it very exciting, but it's striking that 300 years later, we're still in the same place. Okay, 250 years. So on that note, that doesn't mean you shouldn't listen to what I'm about to say. So what I'd like to do this morning is yesterday I spoke about the Lambda Orionis region, which is here. This morning I'm going to sort of walk through a set of star-forming regions to try to introduce you to them. We've already used a lot of jargon. I mean, I haven't counted how many times we've mentioned the word torus already at this meeting. But if you don't, if you're not in the field, you may not have any idea what torus is other than the bull. And we've mentioned embedded young clusters and Orion. So what I'd like to do is at least just sort of paint a broad picture of these regions that we keep referring to, and to give you a bit of context on them. They're only characteristic in the sense that they've been well studied. I wouldn't actually say that in any systemic sense they're really characteristic. It's not even obvious exactly yet what characteristic is. In a sense, that's the point of this school, right? Or at least this subject, to find out what is the typical source of stars in the field, what is characteristic. I'll remind you what we're looking at here. Again, this is the galactic plane, and both Taurus and Auriga lie above the galactic plane, and of course they're also very close. I mean, there's no sense of the third dimension here. Taurus, as you'll see shortly, is a fairly unimpressive star-forming region, except that it happens to be only 150 parsecs away. I forget, was it you, Neil, who said that 150 parsecs was a long ways away? Yeah, so you see, we all have our scales, right? I consider it to be right next door, but...
It's still a long way away.
And then the Orion cloud is of order 400 parsecs away or so. This is the region that I was speaking about last night, and we're going to talk a little bit more about these regions down here today. So this is the area that we're going to be working in today, but it really is characteristic primarily only in being close as compared to anything particularly characteristic about the regions. So this is an overview of what I'd like to cover, but in the spirit of going a bit slower, I think I'm going to actually, especially since Kathy talked about some of the techniques yesterday, I'm going to leave this behind and slow down a little and just really focus on what these regions are like observationally. Actually, now turn off the lights if you would for this one. It's hard not to talk about Taurus without going all the way back to Barnard. Actually, this was published in 1927, but these are the famous images that he took from the early 1900s. And these are the Taurus dark clouds. And of course, just historically, as I'm sure you appreciate, there was a tremendous amount of discussion as he was taking these images about whether or not they were in fact dark clouds or holes in the galaxy. And you can imagine, looking at this region, if you're able to twist your mind out of our particular context, how you could ask that question. This is a somewhat more modern picture just to give you a location. Here's the Pleiades cluster here, and at least in the cloud, in the sky, Taurus is really quite a large region. There are times when I'm at the observatory and it's a dark time, which I rarely get. And you see cirrus going over, and sometimes the cirrus looks a bit like the Taurus dark clouds, or the Taurus dark clouds look like cirrus. They're really very filamentary and very, very stretched out over the sky. This is the Taurus Auriga region. In this case, this is two-mass star counts. So what you're looking at here essentially is, again, a deficiency of stars, of course less so because we're in the near infrared. And this is mapping out in a systemic way the Taurus dark clouds. And the main point of this picture is just to make a point that is perhaps obvious, but nonetheless worth making, is that when you look at the two-mass colors on these locations of few stars, then you see enhanced reddening. And so clearly what we're looking at here are dust clouds. And so this is essentially, if you want a color map of the two-mass data, whereas this is a star count map. This is a molecular gas map of the same region. So I mean, again, just sort of popping back and forth here. You see this sort of characteristic U structure here you can kind of keep your eye on. This is a survey done with the Thaddeus telescope. And basically, you see very similar structure. You see a lot of clumpiness. We've been talking about clumpiness throughout here. And it's been known for a long time that there's a great deal of structure within the molecular clouds here. The total amount of gas is about 10 to the fourth. That's not a lot. So again, this is not a major giant molecular cloud. It's simply very close to us. And as such has gotten a great deal of study. You can see some particular sites of particular high density. But at the same time, of course, you also see regions of very little density. What you're seeing here is a very clear filamentary structure in the cloud. This is the same region with what are known as dense molecular cores marked, and these are essentially numbering the dense molecular cores in each of the clouds. These are the Barnard numbers, the Linz numbers, and then each of these sites is a place where, particularly in ammonia or some tracer of dense gas, you see maybe 2 to 5, perhaps 10 solar masses of material within about 1 parsec or so, 1 or 2 parsecs. They're scattered throughout the clouds. You can also see them in extinction. In fact, Phil Myers and Priscilla Benson originally found these sites as locations of very high extinction, then went after them with ammonia and showed that they were high-density clumps. And as you'll see shortly, when IRAS went up, it became very clear that those were the locations of star formation in the Taurus clouds. And again, so what I'm really doing is walking through here the content of the clouds. This is a recent image from Lumen et al. Essentially, everyone continues to try to get a complete census of Taurus, and every time we look, we find a few more. These days, primarily going down to lower masses as compared to more field or more detections of solar-type stars that we had just missed. Really, with the X-ray surveys, I think we're fairly complete in that regard. But again, you can see a fairly clear correlation between the young stars, some classical T-Tauri stars, some weak-line T-Tauri stars, with the clouds. This clump down here is the L1551 cloud, which has many claims to fame, not the least of which is that the first molecular outflow, bipolar molecular outflow, was found out of this region down here. And then if you go into the infrared, so these are IRAC colors here. These are classic, I'm sorry, I was going to say classic weak-line T-Tauri stars. These are weak-line T-Tauri stars without disks. These are stars with disks. And as you get redder and redder, you're getting more and more into the protostar regime, which essentially means deeply embedded. There's a classification that goes really back to Latta, Shu, and Adams. Class 1, and there's now a class 0 for other systems. Class 3 essentially are fully exposed pre-main sequence stars without disks. Class 2 is with disks. Class 1 is typically has a very strong infrared excess, often is embedded, is thought to actually still be having spherical accretion upon them. And then there's a class 0, which is even more deeply embedded. And basically, the point of this is that occasionally you'll see class 3s scattered throughout the region, but there's an extremely tight correlation of the embedded sources with the gas. And in fact, there's an even tighter correlation of the embedded sources with the dense clumps. So everything, in a sense, hangs together, more or less, as you might expect. So just to give you an overview or a summary of what we know about the Taurus-Auriga region, there's no OB stars, but importantly, and I've always found this to be more important perhaps than some, but this gets back to the issue of the universality of the IMF. The fact that there are no OB stars there is not statistically significant. There's not a lot of gas. There's not a lot of stars being formed, even though they probably have been the most intensively studied. And so the life and the evolution of Taurus-Auriga would have been tremendously different if statistically one O star had formed, which could have happened, but in this case, it didn't happen. And the reason I'm emphasizing this point is because there's an interesting question here about whether O stars form in fundamentally different ways and fundamentally different regions, or whether it's a purely statistical effect. And one simply needs a certain amount of gas and to produce a certain number of stars to have a significant probability that one will form an O star. My own sense is the former. But nonetheless, the fact that there are no OB stars in Taurus-Auriga is not in itself a statement that O stars can't form in such a region as this, because the lack of them is not statistically significant. Again, about 10 to the 4th molecular gas. There's a clear group structure. If you look at where the stars are located with a resolution a little higher than what I've shown, they're not uniformly distributed even across the clouds. In other words, if you accept that the clouds have structure and then look at the location of the stars within the clouds, they're clearly grouped with a mean separation of about 1/3 of a parsec, roughly, which is on the order of a dense core radius. So it's sort of the clumpiness is the structure in the molecular gas is showing up in the structure of the stellar distributions. And typically these groups have of order 20, perhaps 30 stars per parsec squared. So they seldom have 20 or 30 stars, but that's the surface density. And just to remind you of this, Kathy already showed you the Larson slide. There's been a lot of analysis of the structure in the region, but I'll just remind you that this groupness shows up, and whether it's actually fractal or not, as Kathy was pointing out, you can see clear systematics in the structure in these correlation parameters, I'll call them. The structure is not bound. There's other than the multiple star systems, the binaries, there's no structure in Taurus Auriga that is bound. In fact, in some cases, it's not entirely clear that they're bound to the gas, but we sort of take that for granted, so I think it must be true. But this is a very loosely bound system. And when the gas goes away, and that's an interesting question, why the gas is going to go away. There's no OB star. So it's not obvious what's going to drive the gas away. Is it the bipolar outflows? Do they actually couple with the gas adequately to remove it? Is it some sort of galactic effect that's going to go on to remove the gas? Is it an evaporative effect? Unlikely. What removes the gas when you don't have a large energy source is an interesting question, but we presume that it will go away, and when it does, the system will simply dissolve into the field. And then several times it's been mentioned, and I can't tell you how many times in my career, Taurus seems to be an oddball in so many dimensions, and yet it's the most studied region. This is what people have been talking about in terms of the oddity of the Taurus Auriga initial mass function. There seems to be, this is a loosely bound cluster, another Taurus Auriga-like region. There seems to be this excess here of stars in the IMF and the Taurus Auriga region around sort of the early Ks. And Michael, do you want to say anything about that any further? I mean, it exists.
Well, we heard some commentary that most people.
Well, you be sure and let us know. I actually have spent most of my life avoiding the IMF for reasons like this, but I admire those who dive in. Okay, so let me stop there. That's this famous Taurus region. Any questions about that, just as an introduction? Or any additions anybody'd like to add?
I want to comment on those old stars. You mentioned there's no old stars. Is it possible because it's unbound? Because old stars need a longer accretion time. So if the system is unbound, they cannot accrete enough gas to be massive. Or what's possible is it possible then, because I also see some regions that the massive star is a little bit younger than those low mass stars, so they can be formed later.
In other words, there might still be an OB star that's going to form here?
But since it's unbound, so I think it's not possible.
Well, let me be clear about what I'm saying is unbound. The stellar system, when the gas is gone, will certainly be unbound. Whether the clouds as an ensemble and as a complex is unbound is an interesting question.
Oh, okay.
Okay? Because in a sense, we use this word boundedness very liberally, very casually. When you're looking at a structure that looks like this, what does boundedness mean? Right? Do we mean that this entire gas structure in some global sense is bound? Now remember, this is gas. There's pressure here. It's embedded in the interstellar medium. So this is not a purely gravitational system, and presumably it's not going to look like this another 500,000 years from now. But remember, everything is very dynamic here. Or when we say bound, do we mean that these dense cores are bound? The answer there is almost certainly yes. And then do we mean when we have a complex here that the groups of stars that form in these cores are bound to the cores, but the group of stars as a system is not bound? So we have to be careful about throwing around this phrase bound. And remember how I was saying in binaries, it's so important to express what separation scale you're talking about. We should not be using this word bound as loosely as we are, because in systems that are not clearly homogeneous and uniform, that phrase bound needs to be defined over a scale and a location. Thank you.
So is there any kinematic data available? That's what you're talking about.
I'll talk about this tomorrow morning, but the typical internal velocities in this region are around 1 kilometer per second. Between the clumps, between the stars, the internal motions in the clumps are very, very small. They tend to run about 0.5 kilometer per second. So we're talking about very low velocities here. And remember, the size scale we're talking about here, I mean, a typical open cluster on this size scale is about this big, even out to the tidal radius. And a typical velocity dispersion of an open cluster is a couple. So, I mean, this whole system is clearly unbound. All right. Now let's move on to the Orion cloud. So now we were talking about up in this region here. Now we're going to talk about the Orion molecular cloud, which is this really rather famous and characteristic structure here. It's the nearest giant molecular cloud, but it is by no means a notable giant molecular cloud in terms of its size. And by the way, I mean, just again, this picture gives you sort of the full scale of regions that you'll hear names of. The Perseus cloud, the California Nebula, and you see the Rosette is here. I mean, this is just a rich region that happens to be near us that has been explored from both hemispheres extensively. They're all here in this picture. So when we talk about Orion, it really starts with Blau, at least in the context that we're talking about. So let me give you a sense of scale here. Now this is an optical picture. There's Lambda Ori up there. And I think one thing that occurred to me after our conversations yesterday, because many people came up to ask me about that clump of OB stars, again, just to give you a sense of scale, here's the clump that we were talking about yesterday, 10 to 12 OB stars in there. Here's the Orion Nebula. So the main difference between Lambda Ori and the Orion Nebula is that the gas is still here and it's not there. There are as many OB stars in the Lambda Ori association as there are in the Orion Nebula. Okay? I don't think there's as many stars total, although with the dispersion is not entirely, the dispersal is not entirely clear up there. But in terms of size scale, in terms of number of OB stars, they aren't really much different. Okay, so these are the classic associations of Blau. 1A is this region up here. And of course, when you have a deep image, you sort of say, you know, how did he see an association there? But if you just look at the OB stars, it becomes a little more self-evident. So this is the 1A region. 1B is the belt and the scattering in here. 1C is, in fact, a group of OB stars that are projected upon the Orion Nebula but are not part of it, at least by age. Then 1D is the region around the Orion Nebula, and the trapezium region itself is yet another association that was not named. So this whole region, and this is really an essential point that I've been trying to make over the last few lectures, this whole region is rich in star formation and has been for at least 10 megayears. And you can talk about it as associations, or, as I'm going to show next, yeah, let me give you a spatial sense here. Actually, let me not get ahead of myself here. So here's this wide array of associations forming in the giant molecular cloud. And then what we're going to do is move down into this region here, the southern Orion region. So now we're zooming in. And the main point that I want to make with this is not so much all these names, but just to drive home that star formation is happening throughout this cloud. And again, that's the point I was trying to make yesterday at the end of yesterday's talk. This concept of OB associations and T associations, all the historical classifications that we give from the studies in the optical of the field aren't really the point. The point is that throughout this cloud, there's star formation going on. There's a cluster here. There's a massive cluster here. There's an embedded cluster essentially right in there. There's an OB association here. Here's another cluster, 1981. It's an entire ensemble of a star formation complex. And it's only after the fact, after the dissipation of the gas and after the separation of the stars that we start to say, oh, there's an OB association on the sky, let's study it. Because the OB stars are like a flag for it. But all of these other stars, all these other clusters that are going to dissolve, all of this is going into the field. And we need to think of it in that context, not in the historical associations. This is zooming in even further now. This is essentially the Orion Nebula here. And really the main point here is just to show that there's this it's been long known, this north-south structure in the distribution of the stars. This is the variable infrared stars is probably the most comprehensive survey of young stars in the region. They're variable and it's in the infrared, so it's less tainted by extinction. But the real point here is that you see structure in the stars, in the stellar distribution, that mimics that of the giant molecular clouds. And when we talk about as we're going to, the Orion cluster, the nebula cluster, well, it's in here. But where's the edge of it? Right? Again, we classify as human beings these things. It makes it easier for us to talk about them. But it's an entire landscape of star formation in which there's this surface density increase that we call the Orion Nebula region, and then depending on the size of your infrared imager, then you start studying the cluster and calling that a separate entity. But they're all immersed. They're all together in this broad structure that tends to be dictated by the gas. Okay? And remember, everything in there is moving. Okay? Everything is moving. Now, I'm only going to briefly touch on this, but Lynn Hillenbrand did a classic work, and I know there's several of you in the audience who in fact are working on improving and enhancing it. But when we talk about initial mass functions and we talk about age distributions, essentially what we're doing is studying all of these stars, getting colors and luminosities and the like, and typically we place them upon some form of a color magnitude diagram, fit to them some form of a set of isochrones. So this is, if I can read these, this is 10 to the 7th, 10 to the 6th, 10 to the 5th. We then take these stars, we give them ages, we give them, well, you can barely see the mass curves here, I apologize, but here are the mass curves. And then we make plots out of them. And as Michael pointed out yesterday, and I checked Michael, by the way, we did work on the dispersion, but not as well as you do. There's all sorts of phenomena that are adding dispersion to this, such as the binaries, such as the disks and the impact of the disks on the luminosity, such as incorrect extinction corrections or uncertainties in the extinction corrections. This is a hard game to play. Contextually, conceptually, it's straightforward. And of course, underlying all of this are the tracks. And I can assure you that if we used a different set of tracks, we would get a different set of answers, without a doubt. So there's systemic uncertainty in the tracks themselves. So you have to be appreciative of the challenges of turning something like this into something like this. And then we all discuss the universality of the IMF, okay? I'm not saying we shouldn't, but just be aware that it all fundamentally comes down to somebody pointing a telescope in this region and gathering data, reducing the data, analyzing it according to systemic models, and putting all of these necessary corrections into it. That's what made Lynn's study such a heroic effort, because she really was the first who just dealt with every issue possible in a comprehensive systemic way. But even the point is, Lynn is still working on it, and will be, I suspect, until she retires. And then someone else in this audience will pick it up. It's not a done deed, and it's very hard work. In fact, it looks like the IMF that comes out of it looks fairly normal, if you want. I thought Neil made a really interesting point yesterday when he said that what an IMF actually means for massive stars is an interesting question in this school. because necessarily all of the, at least the OB stars, are in star-forming regions. So what does it mean to compare the IMF of a star-forming region to the IMF? Which essentially is what Neil was saying, right? Because the IMF comes from the star-forming regions, the high mass end. The low mass end, of course, has a great deal of meaning from the field. I do want to drive home here just one point about X-ray observations, just to show you the power of what Chandra has brought to this field. X-rays penetrate up to nearly 100 magnitudes in visual. They're incredibly powerful. And the reason that young stars have them is primarily strong magnetic fields, strong chromospheric activity. This is a part of the famous Chandra-Orion Ultra Deep project, just showing you an X-ray image of these young stars in the Orion region. And really the main point I just want to make here, this is X-ray luminosity versus number. And I was just so struck by this curve. This curve are the non-embedded stars. The dashed line are the embedded stars. But they detected 97% of all known stars, that is to say non-embedded stars, in the Orion region with this image. That's an incredibly high systemic success with an X-ray technique. And then the beauty, of course, is that they also get the embedded sources as well. And this just gives you a visual sense of this. This is, of course, the classic beautiful optical image. This is a near-infrared image with the cluster. This is the X-ray image. It's really very powerful. Okay, now if we consider the Orion region as a cluster, this is an interesting thing. Lin and Lee Hartman, decided to fit Qing models to the Orion cluster. This is an absolutely absurd thing to do, okay? But it turned out to be a fascinating exercise. It's absurd because the Qing models fundamentally, I mean, I could teach a whole course on how they fundamentally come from a relaxed solution to the Fokker-Planck equation that Kathy showed the other day. This is not a relaxed situation. What was interesting, though, is that the Qing models, forgetting about the source of the velocity distribution, the Qing model is still a solution of the Liouville equation and the Poisson equation. It's a legitimate solution. And the Orion Nebula is relatively spherical. So even if you don't believe the physics at all, it's still, on a dynamical crossing time type of analysis, is perfectly valid. And they come up with some very interesting results. The core radius of this cluster is about 0.2 parsecs. So we're talking about a very dense region. It's about a factor of 10 denser than your typical open cluster. Now, the other way you might phrase that is, it has permission, if you want, to expand by a factor of 10 after the gas is gone in order to become an open cluster. There's a lot of freedom there, if you want, in terms of its evolution. The central density in the cluster, which is about 10 to the 4th solar masses per parsec cubed, that actually approaches the central densities of many globular clusters. Now, to be clear, the number of stars in the central region is far less than globular clusters, so the likelihood of collisions and all the interesting things that happen in superdense environments probably aren't happening there. But the mass density is not that different from a globular cluster. And then this is essentially what they're doing is doing a dynamical mass here. And the virial mass, as they call it, although I think, frankly, virial is a poor choice of words, the dynamical mass that they get for the system is about 5,000 solar masses. The total census is about 2,000 solar masses. So in fact, unless we have missed a lot of stars, right at the moment, the system is not in virial equilibrium with itself, in other words, with the stars. And in fact, with respect to the stars, it's only borderline bound. Remember, the virial mass is a more stringent requirement than a bound mass by a factor of 2. So to bind this thing would require maybe 2,400 solar masses. Maybe there's about 1,800. It's on the edge of being bound with itself, with the stars. Okay? So what is its dynamic? Yeah, please. Please.
So since the Orion Nebula is elongated, would it make sense to try fitting an elongated to try stretching the Qing profile and fitting it, or does that just mess up all the physics related to it?
No, no, no. It's a good suggestion. I'll show you the elongation in just a sec. They're already using a bit of a sledgehammer to solve this problem. Developing a two-dimensional Qing model to fit the elongated structure is two sledgehammers to solve the problem. I doubt you're going to get a lot of science out of doing that, but it is what should be done. I mean, you're absolutely right. Let me come back to that when I show the image of the elongation. So what is the dynamical state? First off, remember what the very first thing I said to you about stellar dynamics was, the very first thing that I always tell my students.
Stars move.
Stars move, good. What was the second thing? It's time scales, stupid, right? So as beautiful as this cluster looks, and as remarkably well fit as it is by a Qing model, in fact, the typical stellar age of a megayear to within our uncertainties of ages is less than the crossing time, which is about 2 megayear. Okay? So most of these stars, well, in the core, the crossing time is shorter. So you have to be a little careful about these global quantities. But many of the stars that we're looking at have not yet even crossed the cluster, have not actually seen the entire potential well. Okay? It is, in fact, elongated, as you were pointing out, north-south. Remember, though, these pictures are taking away which Lynn well know, are taking away the fact that the entire landscape is elongated. So this elongation comes naturally out of the entire elongation of the entire cloud and system. It's mass segregated. Now, mind you, I didn't say it has energy equipartition. I said it's mass segregated. That means it's a very specific definition, which is that the trapezium especially and the A stars are centrally concentrated. These are, if you believe the mass calibrations, these are the 12 stars with masses greater than 5 solar masses, 90 stars with 1 to 5 solar masses. You notice that the mass segregation is primarily in the most massive stars. It gets much less as you move down to the lower mass stars. If I had time, I would explain this dynamically. This is also true in classical open clusters. It has to do with which stars are determining the potential. But I just want to emphasize that this mass segregation that we talk about is primarily the OB and perhaps early A stars. So whether it's a formation process or a dynamical process remains. I will remind you of what I told you yesterday, is that the equipartition time is much less shorter than the relaxation time. And for this cluster, the relaxation time is about a megayear. So this is why there's been so many papers about whether it's formation or whether it's dynamics, because we're right on the hairy edge. And then finally, the question of whether it's bound. And I already mentioned to you the observed stellar population is 50%, I wish I hadn't said that, of the dynamical mass. But the key is, if you map this region, there's several thousand more solar masses of gas. Now the problem is that the nebula is a blister. It's sitting out in front of the molecular cloud. The molecular cloud is back here, and the Orion region, the nebula, is a blister on the front of the cloud. We don't really know where that gas is. We don't know whether those several thousand solar masses are actually near the cluster and dynamically associated with it and binding it together, or whether it's just behind it and really has nothing to do with the dynamics. Will this thing be bound after the gas is lost? I think we're right on the hairy edge for the cluster as a whole, but as I mentioned yesterday at the end of the stellar dynamics talk, the cores are more bound than the global system. So in my opinion, there's no doubt this is going to make a classical open cluster. Is it going to make a several thousand solar mass open cluster? Frankly, I doubt it. I've been saying that for 20 years, and I don't see anything that has changed. I think it's going to make a small open cluster, which probably will be gone by 10 to the 8th years. And I'll just note, as an aside, observationally, there have been innumerable proper motion studies trying to actually find expansion of the trapezium itself and of the cluster. Some have suggested it, some have not. Those of you who remember the studies in the early 20th century of the rotation of galaxies and the implication of that, I would take this with some caution. This is a hard measurement to make. Hopefully Gaia will do it. Gaia should be able to do it easily.
So, if star formation is still ongoing, evidently some of their gas clouds will be turned into stars,
Mhm.
which means that the imperial balance of the stars themselves might well flip the other way before
It could.
large-scale feedback becomes important.
It could. That's right. There's not actually that much, there aren't that many embedded sources in the nebula region, you know. There's clearly young stars. It's sort of like Lambda Orionis in that sense. There are very young stars there, but there aren't that many class 1 sources, I'll phrase it that way. I mean, there's the Beckman-Neubauer object, but that's almost certainly behind. And so the point that he's making is it may still be forming stars, but in fact we have very little evidence for ongoing star formation in the region. I suspect it only recently blistered, and so that's why we still see young stars. Let me skip this for the moment, although we keep skipping OB runaway stars. They're fascinating, okay? But I do want to get to young embedded clusters, and I think I will probably, I'm not going to rush through this. I'll probably carry it into tomorrow, or maybe Kathy and I will reorganize a little bit. These young embedded clusters are really sort of the new thing of the last decade. They've been really a very important discovery. And that's a phone number I wrote down when my wife called and asked me to call somebody. And for the life of me, I can't remember if I called. I should just call it right now and see who it is. So, definition. There's a classic review by Charlie and Liz Latta. We're going to cut that out of the video. And a very nice review by Charlie himself in 2010. So their definition is that these are systems that are stable against GMC and galactic fields, which essentially is a density of a tenth, a bit more per parsec cubed. Just to give a sense of scale, even 8 to 10 half solar mass stars within a parsec would satisfy this criterion. They want a system whose evaporation time, now remember this is through two-body relaxation, not dissolution, would be longer than 10 to the 8th years. In other words, they want a system that, if it's bound, will last. Personally, I'm not that supportive of this particular criterion, but that's an aside. This is the way they define them. So they need about 35 stars or so to do that. In other words, for a system to last against its two-body relaxation, two-body evaporation for 10 to the 8th years. And currently, it has to be fully or partially embedded in dust or gas. And in fact, very often, the dust or gas mass exceeds the stellar mass in these systems. The embedded cluster phase is of order 2 to 4 megayear. That's certainly not news. And the dissolution time is perhaps of order 10 megayear. In other words, when the gas is gone, given velocity dispersions of perhaps half a kilometer per second, how long will it take for them to essentially not be identifiable anymore? And all of this implies fairly low star formation efficiency. These are two infrared surveys just to give you a sense of the kind of numbers we're at. This survey found 34 embedded clusters within 1 kiloparsec. Remember, Orion is at 400 parsecs, so that's the kind of scale we're talking about, and claimed to be nearly complete. Charlie and Elizabeth did a much broader survey of the sky out to 2.5 kiloparsecs. They think their sample is representative, but certainly not complete. And they estimate about 200 or so within that volume of 2.5 kiloparsecs. That's a lot, considering that we're 8.5 kiloparsecs from the center of the galaxy. And so you consider the entire galaxy, you're talking about, of order 10,000 of these in the galaxy at the moment. Membership is really tough because they have very few members. One is statistical, but again, remember, this comes back to the point I was making before. It's not that you're fighting the background stars here, that is to say the field stars. What you're fighting are the other stars forming in the giant molecular cloud. You're also fighting the background stars, but when you take an infrared image, the question of what's in one of these clusters as compared to sort of the field of the giant molecular cloud is not immediately obvious. if you want to actually know which star is a member of the cluster, in other words, not statistically, not just that there's a surface density enhancement, but that star is a member of the cluster, then you need some evidence for youth. And that evidence can be infrared excesses with Spitzer. About half of them have infrared excesses from accretion disks or enhanced X-ray emission. X-rays really come to the fore here. But again, remember that it's probably also true of the landscape within the giant molecular cloud, this criterion. So the sense of which star is a member of a cluster is much more complex in these star-forming regions than it is for the open clusters that I often work on, where I'm trying to separate the cluster, which has an internal motion of 1 kilometer per second, from a field that has an internal motion of 20 kilometers per second. Now what we're trying to do is to separate the cluster from a field within the giant molecular cloud that has the same velocity dispersion, the same ages, the same properties, and decide which ones are members of the cluster and which ones are just broad star formation in the cloud. It's quite tricky. Yes, please.
So given what you just said, does it even make sense to consider these clusters as separate entities?
Well, in a sense, that's what I've been trying to say all along. They are a surface density enhancement, so they do have a deeper potential well. And so there is a place where some stars are probably bound to each other. And so I think the answer to your question is yes. I think it does. But that said, it is a continuum in which they're living. Please. Yeah. Please.
So Taurus is a surface density enhancement as well.
Mm-hmm.
So, that's what you call an association. I would blindly agree with that. But that's not a cluster. And it's still a surface density enhancement. So is there a critical point in surface density? And if so, does it mean anything physically? Or is it an arbitrary definition?
Well, first, let me just clarify with respect to Taurus. I'll do this with my arms. If Taurus is this big, these embedded clusters are this big. So, but within Taurus, there are clumps of stars that are this big. Typically only of order 4 or 5, and so they would barely satisfy their definition. Okay. Michael, please.
Just a comment, I mean, being a little bit old school, the word cluster means bound. And you could call the aggregates in torus that are still embedded in a clump bound. And if you want to call them an embedded cluster, that's probably fine. I think what Bob's trying to highlight is these things are bound only because the gas is there. And the question is whether they will remain bound when the gas is gone. And they will branch into either being a cluster or an association, be it T or O.
Hurt me.
I would argue,
An unbound system. Well, let's call an association an unbound system. Forget the O and T stuff.
well, that's just about
What's that?
That's just about richness, what the most massive star in the association.
Fair enough. I had always wished early on that Liz and Charlie had called these cluster rings rather than clusters, so we could have had that distinction. Nonetheless, this is very important work, so we're following in their tradition in this. So yes, I actually do think they're significant entities, but do I think they're well defined? I think that's hard. This is just that picture again, trying to show you, the classic. It's funny, when you try to find images of embedded clusters, it's surprisingly hard. They always show the Orion Nebula, which I suppose, anyway. Alrighty, so let's talk a little bit about physical properties here. You've already seen this figure, excuse me, when I was talking about classical clusters. It's really a very, very important figure. So this is the mass of these embedded clusters versus number of clusters. This is the actual population here, and this is an additional population of large clusters over a larger volume found by Dr. Asenso, and I apologize if I've pronounced that wrong. Because in the original distribution, there was a real question of if there is a power law here, where are these high clusters? And some have been found, although it still seems like there's a fairly large number that have not been detected. And I'd be interested to get the input from the experts in the field on that. There's also a turnover here which seems to be real, but we're down to very few stars. And if one then adds a concept called groupings, such as, for example, in Taurus or Ryga, you can fill this stretch in, those are almost certainly immediately unbound. There's an interesting issue with the slope here, in that if the slope here was -2, you actually end up with equal mass per decade. Or to phrase it differently, the probability of a star forming in any particular size cluster is equal. Now, the actual slope here that they find is more like -1.7. So that's not strictly true. But I think it's an interesting concept, because if you're going to ask where is a star most likely to form, or do most stars form in clusters, this slope of -2 would actually make that question even more intriguing, because then the question is, it's an equal probability essentially in clusters of all masses. So it's just an aside. Please.
I'm sorry, this is the wrong concept of probability. The most likely cluster to form is a low mass cluster. Is it not right?
Yeah, equal mass.
Equal mass per decade.
But if you ask a given star, where is it most likely to form, it's most likely to form in a low mass cluster. But if you ask where is most of the mass in the star population coming from, it's equally distributed.
No, but you have,
So it's a different question.
if every star is one solar mass, 10,000 form in these few clusters, and 10,000 form in these more numerous clusters of only 10.
No, because it's the square. Well, perhaps we should discuss this.
Sure,
offline,
yeah,
but
no, that's fine. We'll talk about it offline.
Versus mass.
It's number versus mass.
Mhm.
Whether you have an extra end in the interval.
But we probably should wrap.
Absolutely.
this up.
That's fine. Okay, I'll stop here and we'll pick up embedded clusters at the beginning of the next lecture. Good.